Hi everyone. So in today's lecture, I just want to go over a few things that I kind of ran out of time on the last slideshow. And I wanted to give them a little bit more explanation than running through them so quickly. So we're going to focus on how we measure toxicity. So we've been talking a lot about chemicals that could be harmful and that maybe persist in the environment. So we need some way to figure out, well, how toxic are they? So our main thing that we're going to focus on is the LD50, okay? But before we get to that, I just want to go over a few details. So one of the things that's challenging is figuring out how to determine how these things will affect humans, okay? And there's a couple different ways that people can study these in humans. So one is just taking case history. So if somebody comes in and they have a particular disease or problems, you take a case history and try to figure out what they might have been exposed to. The problem is this really doesn't give you an idea of, maybe small exposures over long periods of time. It's not really good for figuring out those small details. All right, so the next study would be an epidemiological study. So I know some of you are taking or have taken epidemiology. So that's basically the idea that we're going to compare large groups of people, so people that have probably been exposed to those that haven't, over long periods of time, okay? And try to tease out what the effect of just that particular thing is. And that's really hard to do because obviously we're exposed to a lot of different chemicals and a lot of different environmental conditions. And some of these things, let's say you have a cluster of leukemia cases in a given area. Well, the incidence of leukemia is pretty low to begin with. So even if it's a little higher than normal, we're still talking not huge numbers. And the other thing is that sometimes just through chance, you get clusters anyway. And so just because there's a cancer cluster does not mean that it's necessarily caused by one thing. So what epidemiologists rely on is they go back and use various statistics and try to see if they can figure out how strong the correlation is between exposure and whatever particular cluster they're seeing. If anybody's interested, I think it was last summer or the summer before, I read this really good book, Tom's River, Story of Science and Salvation by Dan Fagan, and it actually won a Pulitzer Prize. So it's talking about Tom's River area in New Jersey. So New Jersey in general had a lot of issues with various industrial pollutants. And this is a story of basically pollutants that got into the water table and polluted people's well water. And this was literally like a decades-long studies of trying to figure out what the repercussions of this was. And he goes into really good details about how the epidemiological studies were done. So I highly recommend it. But anyway, so these first two things, as we can see, have some limitations. So a lot of times what people fall back on is animal models. So usually this is going to be mice or rats, things that are easy to raise, and that you can see over long periods of time. So animal testing, we can see what the effects are on animals and then try to determine what that might be on us. So we try to pick animal models that are going to be close to how our systems would deal with the same chemical. All right, and I just wanted to go back. I know I mentioned this really briefly. I was running out of time in the last video, but one of the studies that was done in the Yaqui Valley in Mexico was comparing two populations, one of which had switched to using pesticides on their agriculture and one that didn't. And they didn't really have enough money to go and do like blood tests and figure out who had the pesticides. But what they did instead was they looked at drawings by children. So they compared the children in the foothills who were not exposed to the pesticides versus ones that were. And you can see just from here what the difference was. So this study seem to indicate that there were clear developmental problems with exposure to this particular pesticide. But some criticisms of the study were that they didn't, since they didn't know what the blood content was, and they didn't have a way to really figure out what the exposure levels were, that you really couldn't reach like a causation from those two. But it definitely makes you wonder. Okay, so what I really want to talk about now are animal studies. And so these are good because we can figure out what the effects are. Things like mice or rats have much smaller or quicker life cycles, so we can figure out the answers a little bit quicker. The problems is that we have to make some extrapolations. So we have to think about, well, okay, if this much affected mice, how much would the similar dose be for humans, for our body size, for instance? We also have to make assumptions that our bodies would respond in the exact same way. And so we're still mammals, so we have a lot in common, but there are always little quirks that maybe a rat or a mouse doesn't respond in the same way. So that can lead to complications as well. But this is pretty much sort of the hallmark way that people look at toxicity. So what do? So they construct something called a dose response curve. And the idea is that you start with very low doses and you increase the dose. A lot of times this is done by like orders of magnitude. So you would dilute by like tenths. All right. So you have a large range of doses. And then you look at the percentage of your test population that dose is lethal for. Okay. And so then you can plot it is percentage that it's lethal versus the dose. Okay, and then if we go, so 100% up here on the curve, if you go to 50%, so this is 50% of your test population, that particular dose is lethal. You can come over on your graph, see where it intersects with the curve, and then if you go down, this gives you the dose. So that dose is termed the LD50. So that's the dose that kills, or the dose that's lethal to 50% of your population. Okay, so it's just similar to in biology when you think of like KMs. So the units here are units of dosage. So how much of something is lethal to 50%. And this particular one is showing a linear dose response curve. So this is kind of your classic dose response curve. And it makes sense. As you get bigger doses, you would expect larger lethality. Okay. Sometimes what you see though, instead of that absolute linear, is you'll see that really low doses don't have a response that we can measure. All right. And so this is termed the threshold, where below this dose, there's no response. And above the dose, you start to see a response. Okay. So now we have the LD50, which you can still see over here. And you can also now identify a threshold dose. Now remember, this is just whether we can see it or not. It doesn't necessarily mean that nothing's happening down here, but at least given our testing procedure, we are not seeing any effect. Does that make sense? Okay. All right. So what are some of the problems with these dose response curves? So I was showing you basically the classic ones, but there are a lot of times where people will get nonlinear curves. So it won't really do what we expect. Sometimes you'll actually see increasing effects with increasing dose, and then it drops off. All right. Or in this case, so this is, I don't think you can see it, but this is the dose of bisphenol A. So this is looking at BPA. And here, instead of looking at lethality, we're just looking at percent of mice with chromosomal problems. So instead of calling this the LD50, we might call it the ED50 for effective dose. So we're not looking at lethal, we're looking at some particular effect. But notice, if you kind of can connect these dots, this is not linear. It's kind of going to level off. And we see that a lot with endocrine disruptors. So endocrine disruptors, remember, are mimicking hormones, and hormones are going to have effects at really low levels. So that's why you see this increasing here. But once you get to a certain level, you're going to get to the point where increasing hormones not going to be able to bind to any more receptors, so you don't see an increasing result. And in fact, with some hormones, it actually might drop off after this. So that makes this a little bit more complicated. The other thing that people are starting to look at are synergistic effects. I think maybe Poison Waters might have mentioned this, but this is the idea that the sum of two things is the overall effect of two things is greater than the sum of their parts. So you may have two chemicals, chemical A and chemical B, and if you look at both of them separately, you're not seeing an effective dose. But if you put the two together, even though individually they don't cause a problem, if you look at them together, they may cause a problem. So they act synergistically. All right, I hope that makes sense. Okay. And just wanted to briefly mention regulation. So there are regulations for various chemicals. Part of the problem is keeping up with especially new chemicals and also chemicals that are really old that have been kind of grandfathered in that we may have been using and not really had data on. But the EPA, the Environmental Protection Agency, regulates industrial chemicals in the U.S. So this would include things like pesticides. So you may see articles where the EPA is trying to figure out whether to ban the use of chlorpyrifos, for instance. And so they're looking at what their data show and how they should regulate that. Internationally, there are also other agencies that regulate these. So in the European Union, they have the REACH program that does similar things to the EPA. One of the differences is that the REACH program, they make the industries prove that something is safe before it's used, where a lot of our chemicals, we adopt a more wait and see attitude. So slight difference on how we regulate those. And then one of the big conventions was in 2004, there was the Stockholm Convention on Persistent Organic Pollutants. So persistent means these are pollutants that don't degrade in the environment. So they hang around for a long time. And organic, right? So that's organic chemicals, carbons and hydrogens form the basis of a lot of these. Okay. And so what the Stockholm Convention did was it identified what they call the dirty dozen of persistent organic pollutants, or POPs. And these are the things that the Stockholm Convention, in trying to do everything, they tried to focus on some of the most egregious polluters. And so you can see some of these you recognize, right? Here's DDT. You may recognize dioxins. Some of these are pesticides like heptachlor. This was something that I believe Rachel Carson also talked about. And then PCBs. So these are a big industrial chemical that were used for years. So in the Seattle area, for instance, Boeing used these. And some of these have polluted our waterways. And they last for a very long time. So some of the sludge on the bottoms of these rivers, for instance, still have PCBs, even though they may have been not used for decades. So there are a lot of research that's going on to how to figure out, like, are there ways maybe we could use bacteria to break these down now, because they really are very persistent in the environment. Okay, so I think that's it. That should tie up a lot from chapter 14. Go ahead and make sure you read through it. There's a lot of other things that I might not have gone into a lot of detail, but I thought I'd pull out what I thought were the most important things. So hope you're having still surviving at home okay, and have a good day. See you later.